let's get started. Okay. Can you see the slide? Okay, good. All right. In the last class, we have discussed about generation. Okay, generation process. Before that, we have covered thermal equilibrium in intrinsic semiconductor, in N-type semiconductor, and in P-type semiconductor as well. And then we move to discuss about excess carriers, in which we introduce new carriers into the system, okay, into the semiconductor material on top of the carrier density at thermal equilibrium. Right, there are a few ways that we can use to generate excess carriers. For example, in this slide, you can see we can use optical excitation, for example. This is what we use in solar cell, where we use incident light or incident photons in order to generate electrical energy out of it. We can also use electron bombardment by using electron beam, and we can also use doping. Okay, we can also use doping, where we introduce p-type or n-type dopants into the semiconductor material in order to alter its conductivity. And then we discuss about this. The new carrier or the new density of electrons or the new density of holes is given by the electron concentration at thermal equilibrium. Okay, electron concentration at thermal equilibrium plus the excess carriers. Okay. On the other hand, for holes, the new density of holes will be given by the density of holes at thermal equilibrium plus excess carriers as well. And we have also discussed that when we generate excess carriers, the value of delta N and delta P will be equal. Because, why is it so? Kenapa value delta N, delta P sama? Anyone? Okay, discussed last time. Why do we have the same magnitude of delta N, delta P? Electron hole pairs, right? Yep, electron hole pairs. Okay, because they will impair. And we have also discussed about carrier injection, where we assume our semiconductor is N-type in this case. Okay, injection, and we assume our dopant is N-type, and therefore since the ND is given, so the silicon here is N-type and N0 is equal to ND because we assume 100% ionization. And therefore P0, the minority carrier concentration, will be 10 to the 5 because we use this equation, N times P equals to Ni squared. So since N0 is 10 to the 15, P0 will be equal to 10 to the 5, since Ni is equal to 1 times 10 to the 10 per centimeter cube at thermal equilibrium, right? So in order to calculate the new concentration of electrons and holes, we need to use the the equation on the previous page. Assuming delta N and delta P equal to 10 to the 12, right? So for density of electrons, so that is given by N naught plus delta N. So N naught is 10 to the 15 given by ND, and delta N is 10 to the 12, and the final value of N, or the latest, the new value of density of electrons, will still be equal to the doping concentration, right? The dopant impurity level, which is equal to N naught. Sorry. Okay, on the other hand, if you use the same equation for P, which is equal to P naught plus delta P, so the final value will be approximately equal to the excess carrier value, right, delta P. So we'll not see any change in the majority carrier, but we'll see some change in the minority carrier, right? So this condition is called low level injection, because what you introduce into the system doesn't affect the doping concentration or the density of electrons or the density of majority carriers, right? Density of majority carriers is not affected, and this is called low level injection. However, when you introduce your delta N or delta P to be at comparable level to the majority carrier concentration, it will be called high level carrier injection. And in that case, it will change the density of majority concentration. Okay. So today we're going to look at carrier generation by absorption of light, right? So we've covered in the previous slides about optical excitation, and this is exactly how to do it. Optical excitation, right? When you shine light on your semiconductor material, and we'll see absorption of the light and excitation of the valence electrons into conduction band. Right, on the left hand side is the indirect band gap semiconductor. So you can see that the minimum point in the conduction band, as we discussed last time, is not aligned to the maximum point of the valence band, right? So they are at different crystal momentum value, right? So the x-axis is different, so they are not aligned, and therefore they're called indirect band gap semiconductor, like silicon, germanium. Okay, so on the other hand, on the right hand side, we can see the band gap of direct band gap semiconductor, where the minimum of the conduction band is aligned to the maximum of the valence band. In this case, called a direct band gap semiconductor, like gallium arsenide, cadmium telluride, indium phosphide, and whatnot. Okay. So now we're going to look at photo generation of electron hole pairs in both. Right? Photo generation here means generation of electron hole pairs by using light. Okay, we use light in order to induce generation of electron hole pairs. So we discussed last time when we talk about transition between valence band to conduction band, we have discussed about transition number 1, where the valence electrons is excited into conduction band, and transition number 2, where the electron recombines with hole in the valence band. Right now we're talking about transition number 1 on the left, right? Transition number 1, where the valence electron is excited into the conduction band by the incoming photons or by the light. Okay, so the photon flux within the material is given by F there, Fx there is due to the photon flux. Photon flux is equal to F naught or F0, exponential negative alpha. Alpha here is the absorption coefficient. We're going to see in the next slide. Absorption coefficient, abs coefficient, and X here is the depth into the material. For example, if you talk about katalah this is your cross section of your silicon, so the F naught is the initial flux, initial level of the flux when it starts hitting the semiconductor material, and the value of the flux inside the semiconductor will be dependent on the absorption coefficient and the depth, right? So that will define the level of flux within the material, right? So from the flux within the material, we can calculate generation rate. Okay, photo generation or generation rate. So photo generation here means generation of electron hole pairs by using the incident light. Okay, the photo generation rate of the electron hole pairs is given by Gx, right? The photon is now the flux, so the photon is given by Fx, and the generation rate is given by Gx. And Gx is given by absorption coefficient times the flux exponential to the same component, right? Exponential of the same component. Negative negative absorption coefficient times the depth of the flux within the material. Okay, so that will give you the flux and the photo generation rate. Okay, remember photo generation rate is the creation of electron hole pairs. Yeah? Electron hole pairs. Generation to create electron hole pairs. So we call it as a generation process. So that's why in this topic we call it generation and recombination. Generation is when we have transition number 1 on the left, where the valence electron is excited into the conduction band, and recombination is the opposite process. Right. So what is happening when light is incident on a surface? Apa jadi dekat cahaya bila dia melanggar permukaan, satu permukaan? For example, if you talk about our daily life, kalau you tengah, if you're combing your hair, for example, if you're in front of a mirror, apa jadi kat light tu sebelum you can see yourself? Anyone? Can you explain this phenomena when you're in front of a mirror, for example, every day? What is actually happening in front of the mirror? Anyone? Cerita sikit apa jadi kat depan cermin. Reflection, okay. Haziq cakap reflection. Lagi? Juwaria, what's happening in front of the mirror every day? Okay, reflection of your image. What's happening before you get the reflection of your image? Apa jadi kat cahaya tu? Okay, you must have light. Okay, so when you have the light, then so you have a light source. For example, you have LED lights in the room. Then apa jadi? So when the light is on, so what happens next? Syafiah. Apa jadi? Light dah on sekarang. So, apa jadi kemudian? Kita duduk bersiap tiap hari kan? So, what is happening in front of our mirror every day? Anybody? Yes, light is reflected. So light is reflected. But before the light is reflected, apa jadi, Rafael? So you turn on the light. So light is reflected from. Sebelum dia reflect tu apa jadi tu kat light tu daripada LED tu? Is coming off the LED. Is incident on. Okay. Okay, transmission, you said transmission. Okay, the light is inside. Hold on. Farhan said light is incident on. Elaborate a bit. Where is the incident? Surface of the what? Of the mirror, right? We're talking about mirror, right? So the light is incident on the mirror, then is it light is reflected off the mirror. So what happens to the reflected light? Let's track the journey of the photon before you see yourself. Ada belajar kan dalam optik kan? Belajar lo 215. 215 ke? Is it 215 or 21 something? I don't remember. So lepas reflected, apa jadi dekat light tu? Inverted. Okay, yup, forming the image, alright. Okay, bila light reflected off the mirror, light tu pergi mana? How do you see yourself in the mirror? Light yang reflected off the mirror pergi mana? Transmitted pergi mana? Haziq? Ke mata, masuk mata tu reflected ke transmitted? If you look at the figure on the left here, incident, reflected, the hijau kuning ni, image yang hijau kuning ni. So yang mana yang masuk kat mata? Absorbed and transmitted to our eyes. Okay, light is reflected to our eyes, right? Reflected to our eyes. So you are in the front here, in the front of the mirror. Okay, so for example, if you look at a wall, for example, and the wall is yellow. Okay, kenapa you nampak color yellow tu? Katalah you masuk dalam lecture hall and the color of the wall is yellow. Why do you see the yellow? Okay, reflected, inverted about the y-axis, right? Why do you see the yellow, for example? You enter a lecture hall because yellow is absorbed, because the material absorbed all the other wavelength, right? Yeah. Okay. So why do you see yellow? Because other colors are absorbed by the wall and yellow is reflected. Okay, yellow is reflected, so that's why you see the yellow. Sebab color kuning tu, the yellow is reflected. Then we see the yellow reflected into our eyes. We see the yellow, so that's how you get the color. Okay, that's the principle. Okay, so the same is applicable to any incident light on any surface. So when the incident light is incident on a surface, for example, if you look at the one on the left here, the figure on the left, so you can assume that the incident light has the incident light, say it has 100%. Yeah, money it comes as one lah, as one, so that's why it's called 100%. So when the light is incident on a surface, so in this case we're talking about semiconductor, so let's assume it's silicon. So some portion of the light will be reflected. Okay, it's incident and then some portion will be reflected. Okay, so what is not reflected? Say the reflection is about 20%, for example. So if 20% is reflected, how much will go into the material? So you have 100% and 20% is reflected. How much is left to go into the material? Simple math. 80%, right? Cool, 80%. Simple. So you have 100%, and upon the incidence, 20% is reflected and gone. Gone. Habis, hilang. So you're only left with 80% of the incident light, right? Compared to the original 100% tadi lah. So you're only left with 80%. You are left with 80% of the incoming light. So of the 80%, then the 80% will go into the material, and some portion of the 80% will be absorbed. Okay, some portion will be absorbed. So let's say out of the 80%, mungkin say 20% je, 60% je yang absorb, right? And then the other, how much more is left? This one is simple calculation. Don't think about the wavelength dependent and whatever yet. Just simple illustration for you to understand. So we have 20% that is not absorbed, that is transmitted through the sample. Keluar kat belakang, right? Keluar kat belakang. If I have this silicon, for example, so I have incident light of 100% here in the front, then 20% is gone, and I have 80% going into the silicon, and out of the 80%, 60% is absorbed, and you are left with another 20%. No, 20% that is not absorbed will be transmitted through the sample. Okay, transmitted through the sample. Okay, maknanya dia tembus kat belakang, leaking through, right? So this is what I call a simple principle to illustrate reflection, absorption, and transmission mechanism through your semiconductor material, right? So we're going to see later on how absorption of light takes place. Right, before that, let's see the figure on the right first. See, out of the 100% of these three colors, for example, if you assume these three, then the one on the left will be all reflected, and the one in the middle will be all absorbed, and the one on the right will be all transmitted. Okay, so let's see what actually happens when the light is absorbed. Let me share the page with you so that you can see the animation. Where is the thing? What's the page? Okay, it's active, but okay, cool. It's here. Okay, can you see the website? Okay, good. Right, you can come to this PVCD-ROM and go to absorption of light. So under 3.2, section 3.2, generation. So you can see absorption of light, absorption coefficient, depth, generation rate. So this is exactly what we are going to cover in this topic, right? So let me just keep all this up here. So what will happen when the light is incident on a semiconductor material? So there are three cases that you have to consider, right? So the first one is here, when the photon energy of the incident light, so incident, the light is made of photons, so, and the photons have a range of different energies, so depending whether they are UV photons or visible, and the visible you can even divide into multiple colors, and UV or visible or IR, and they have reducing energies, right? From UV to visible to IR with increasing wavelength. So if the photons have energies lower than the band gap, so let's assume that the silicon material is being used now, so the band gap is 1.12. So case number one, if the photon energy is less than 1.12, well, what will happen is photons with energy of less than the band gap energy, less than 1.12, interact only weakly with the semiconductor material, or with the silicon in this case, passing through as if it were transparent. So if your photon energy is less than the band gap energy, all the photons will just pass through the silicon as if the silicon were transparent. So that there will be no absorption at all, right? Since you're talking about absorption and generation now. Okay, so case number two. So case number one, it was transparent. Case number two, what if the photon energy is equal, right? Has the right energy, just like the energy of the band gap, right? So that means the photon energy is 1.12 electron volt, just enough. So just enough, the keyword here is just enough to create electron hole pair and efficiently absorb. So when the photon energy is equal to the band gap energy, the photon will be absorbed, or the light will be absorbed, and the valence electron will be excited into the conduction band. So then you're going to have a generation of electron hole pairs. So there will not be any generation of electron hole pairs for case number one because there is no absorption at all, right? So that's case number two. So how about case number three? Case number three is when the photon energy is more than the band gap energy. So in this case, the photon energy is more than 1.12. The photons with energy much greater than the band gap are strongly absorbed, so they are still absorbed. However, let me read this. This one is more for the solar cells. For solar cell application, the photon energy greater than band gap is wasted as electrons quickly thermalize back to the conduction band edges. Okay, so what will happen when you have photon energy greater than the band gap energy? There will still be light absorption. That means you're going to get generation of electron hole pairs as well. But the energy that you have is more than what you need to excite the valence electrons. So what will happen is the extra and the excited electron will be excited further up into the conduction band instead of just at the band edge. Then it will quickly thermalize back to the conduction band edge due to thermalization effect, right? So let's see what we mean here for all the three cases. So let's see case number one, then number two, then number three. Okay. So now EPH less than EG, photons coming into silicon, and nothing is happening, right? So watch here, this is the valence electron. So it's not excited into the conduction band because EPH is less than EG. So in this case, the silicon will behave as a transparent material to the incident photons because the energy of the photons are not enough to excite, right? To excite. So let's go to case number two. EPH more than EG. All right, so this one is case number three already. EPH more than EG. So the high energy photon gives its energy to the electron moving up to excite electron into the conduction band, but further up, not only up to the band edge, but further up into the conduction band, and leaving a hole behind in the valence band. So what happens next is thermalization, right? Electron hole pair releases thermal energy and relaxes to band edges. Excess energy is wasted, right? So what's next? So this is the case number two. Okay, case number two, a photon with energy equal to, right? There's no excess energy at all because you just have the right amount of energy to excite the valence electrons into the conduction band. So the photon with energy equal to the band gap is efficiently absorbed and there's no heat wasted. So the excitation takes place from the valence band right to the band edge of the conduction band. So there's no thermalization at all. Okay, so is it clear? Can you see that now? All the three cases? Number, okay, is it okay? Okay, right, good. So these are the three cases when the light is incident. You can always come here and animate yourself. Okay, let me continue now with the slides. So that's exactly what happens when you want to absorb the light, right? So reflection is governed by some other thing, like Fresnel reflection. Last time we discussed about R equals to N1 minus N2 over N1 plus N2 squared, right? Fresnel reflection. And absorption is governed by the one that we talked before. Three cases: EPH less than EG, EPH equals to EG, and EPH more than EG. Right? So the light absorption will only take place when EPH equals to Eg or EPH more than Eg. So when the EPH is less than Eg, the semiconductor material will behave as a transparent material to the photons. Walaupun if you look at the silicon wafer, for example, it's not opaque, right? So it's not transparent. It's not transparent, right? It's opaque. It's opaque. It's not transparent. However, photon pada wavelength tertentu, photons at certain wavelength will be transparent to the material. Okay, even though the material itself is not transparent. Okay, so then you have to understand this concept when the EPH is less than Eg. Okay. Right, so absorption coefficient, the alpha value. So we talk about alpha just now in the flux and photo generation rate equations. Alpha here is the absorption coefficient. So what is absorption coefficient? Alpha or absorption coefficient determines how far into a material the incident light of a particular wavelength can penetrate before it is absorbed, right? So alpha will determine how far your incident light of a particular wavelength can travel into a volume of material before it is absorbed. Okay, kalau dia nak masuk ni, katalah you ada material yang tebal, and this is your photon, for example, of wavelength X. So some other the photon is absorbed near the surface or in the middle or at the back of the material, depending on the thickness, will be dependent on the absorption coefficient, right? So it determines how far the incident photons is absorbed into the material. And you have to know the alpha and you have to know the wavelength of the incident photon as well. So low alpha means the light is poorly absorbed, right? So if you talk about low alpha, we're talking about light will be poorly absorbed, and if the material is thin enough, it will appear transparent to that wavelength. Okay, so when you talk about light absorption, we are talking about volume of material. Okay, volume of material interacting with the incident photons. So what do you think? If we have a thicker material or a thinner material that can absorb more light? Do you need thicker material or thinner material to absorb more photons? Thicker to absorb? Thicker, right? Okay, thicker. Okay, you need thicker material. Kalau ni saya punya scientific calculator. So if you look at this cross section, kalau you ada banyak photons kat atas ni lalu incident, and then the material is only thin, so you know the volume is not enough, the thickness is not enough for the photon of respective wavelength to interact with material before it is absorbed, right? So there'll be light material interaction. In comparison to some other semiconductor material with perhaps double thickness, kalau saya letak phone kat bawah ni, so the very same photon of different energies, just like the first case, dia ada banyak lagi, dia ada banyak volume yang dia boleh go through in order to interact with the semiconductor material. Hence will determine the absorption of light. So you can compare this to washing dishes. Semua pernah basuh pinggan kan? So have you ever used the sponge to wash your dishes? Mestilah pakai sponge kan, unless you use a dishwasher, right? Kalau you ambil sponge, I don't have the sponge now with me. It's in the kitchen. Kalau you ambil sponge yang sama, if you're taking a sponge of the same width, kalau kelebaran ni sama, lebar sama, the width is same. You have sponge now, okay, good. Right, try to compare. If you have sponge one, a very thin one, kalau kita, if you look at the sponge in the kitchen, then normally the green one, right? The green one, the thin green one to nak rub the periuk ke apa kan, yang kasar gitu. So that's the green one. And sponge number 2, you take the very same. Kalau ada tu you tunjuk kat display ya, Haziq. Apa ni? Okay, sponge number 2, you ambil sponge yang sama with the same width, but then the yellow one, right? Kita ada green and yellow, right? The common one that we see in the market, right? Green or red, I think, and the other one, the yellow, the thick one, right? Which one, the green or the yellow, can hold more water? Kalau you rendam dalam air, which one
Yellow,
can hold
Doctor.
more water? Yellow, right? So the same principle applies here. So yellow can hold more water because it has more volume to handle. So the same goes to the volume of semiconductor material interacting with incident light. So in this case, the sponge is your semiconductor material, and water yang you nak squeeze tu, you nak absorb tu, will be the incident light, right? So of course the yellow one, the thick one, can absorb more. So the same goes to the silicon or other semiconductor material as well. So the thicker that your semiconductor material is, the more light it can absorb, right? So in this case, if the alpha is low, but you have silicon sample number 1 thin, but silicon sample number 2 very thick, but both have the same alpha, both have the same absorption coefficient. So that means more light will be absorbed in the thicker silicon compared to thinner silicon, right? More light will be absorbed in the thicker silicon compared to thinner silicon, even though they have the same alpha. So the volume will make the difference, right? Alpha depends on the material and also on the wavelength of the light being absorbed. Okay, we'll see later on as well. Semiconductor material have a sharp edge. Okay, you can see this later on. Let's just go through this page and I'll stop. Absorption coefficient still. So the absorption coefficient in a variety of semiconductor material at 300 Kelvin is shown in the figure down here. Right, crystalline silicon is an indirect band gap. So we've discussed about direct band gap, indirect band gap before. We know that crystalline silicon is an indirect band gap, and germanium is an indirect band gap. Amorphous silicon is direct band gap. Gallium arsenide, cadmium telluride, what else? Indium phosphide, they are all direct band gap materials, right? If we talk about indirect band gap semiconductor like silicon, germanium, in this case, the example is silicon. It is a poor light absorber. Okay, poor light absorber because it has an indirect band gap material. So when the band gap is indirect, it is a poor light absorber because the alpha is low. Right. So let's compare here. Let's compare silicon. In this case, crystalline silicon is the red one. Okay, is the red one. Let's compare that with gallium arsenide, the blue one. So let's pick wavelength of 600, for example. 600 nanometer. Look at the absorption coefficient for crystalline silicon there on the y-axis and gallium arsenide there as well. So silicon has alpha of about 10 minus 3 at 600. Okay, so that's about 10 minus 3 per cm, whereas gallium arsenide has 10 to the 4. Right, gallium arsenide has 10 to the 4. So that's like 1 order of magnitude higher for gallium arsenide due to its direct band gap nature. Okay, so this causes the crystalline silicon to have a poor light absorption. Maksudnya, if you want to use crystalline silicon for solar cell, for example, because solar cell operates based on light absorption, if you want to use crystalline silicon for a solar cell, that means you need to use a very thick material, very thick D, say D is the thickness of crystalline silicon in order to absorb most of the incident light. Whereas you might need only a little bit of gallium arsenide to absorb the very same amount of incident light. Okay, so this will determine the quantity of material needed in order to absorb most of the light, right? So in this case, if you talk about indirect band gap silicon, indirect band gap material like crystalline silicon, normally for solar cell we need to use close to 200 micron for light absorption, and even that is not enough yet. 200 micron for silicon solar cell, and if you talk about gallium arsenide, you may need only 1 to 2 micron in order to absorb most of the light. So that's the what I call the difference in the magnitude needed. Okay, due to the effect of indirect band gap or direct band gap that will lead to low alpha or high alpha. Okay, so indirect band gap or direct band gap contributing to the alpha, which determines the absorption of light, whether it's good or not. So that will then determine the volume of material needed to ensure most of the light is absorbed in your specific application. So in this case, the example is solar cell because it's based on light absorption, which is then converted into electricity out of the device. So this is what it needs, right? So you need only about 1 to 2 micron of gallium arsenide because it has high alpha value. On the other hand, you need about 200 micron of silicon because it has low alpha value. Then later on, when we talk about device, we're going to discuss about, then if that's the case, if the gallium arsenide is so thin in order to absorb most of the light, and silicon has to be so thick in order to absorb most of the light, why does silicon dominate most of the PV market? Silicon dominates 90% of the photovoltaic market. Why not gallium arsenide? Why not some other direct bandgap materials? So that will be discussed when we talk about devices. Yeah, cost and many other stuff, volume, knowledge of microelectronics and stuff like that, right? So we're going to stop here now and let's continue tomorrow with absorption depth and so on. Okay, so is it okay so far? Light absorption, is it clear? Light reflection, transmission, photon energy less than, equals to, more than, bandgap energy, thermalization, and all the stuff. Okay so far? All right, good. So I'll see you tomorrow. Tomorrow's what? Tuesday? 10 a.m., right? So I'll see you tomorrow, 10 a.m. Okay, bye-bye. Take care. Assalamualaikum. Stay safe.
Thank you very much, Doctor.
No worries.